So one more article in this particular unit. This unit is full of articles. This is the last one. So do enjoy it. Torque, or better to say, try to enjoy it. Experienced by current carrying rectangular loop inside a uniform magnetic field, right? Torque experienced by current carrying loop inside a uniform magnetic field. Let us consider a uniform magnetic field. Perpendicularly inward to the plane. Magnetic field is perpendicularly inward, right? I am placing a loop, a rectangular loop, right? Place perpendicular to this field means both are the perpendicular side, not only the length and the width. This is, just name it P, Q, R and S, right? And I is the current flowing through it. Let the length of the loop be L and width be B. So when a current carrying loop, rectangular loop, is placed inside a uniform magnetic field, what happens? It starts rotating. This is the practical aspect. It means a torque is acting on it, which is trying to rotate the loop inside the magnetic field, right? Our aim is to calculate that torque. So let us consider a loop PQRS of length L and width B placed inside a uniform magnetic field in a direction perpendicular to it. So what will happen? We will try to assess that. So this loop consists of 4 parts: P, Q, R, S and P. So we will try to calculate that, as we have the force experienced by a current carrying wire inside a magnetic field is given by IBL sin theta, the first article of this chapter. This is the force experienced by a current carrying wire placed inside a uniform magnetic field. So by using this, what will be the force experienced? So force experienced by PQ segment of the loop, FPQ. What will be FPQ? Formula says current I, magnetic field B, length is L and it is placed perpendicular to sun 90, right? So it will be IBL. What will be the direction? Apply that rule, Fleming's left hand rule. Direction will be like this, means a force is acting on it in this direction, FPQ, right? Away from PQ, right? Similarly, if I calculate FRS, that is again the length part, current is I, magnetic field is L and L sin 90, right? Or it will be IBL. But now the direction of current is downward, so it will be away from RS. It will be like this, FRS. What about FQR? FQR. FQR will be I, B, length is now B, sine 90. It is I, B, B, like this. Direction will be in the upward direction, like this. FRS. What about FSP? If S is, this gap is very small, so what will be FSP? It will be I, B, B again, and out, downward, like this. So what happened actually to the practical aspect, that the line of action of this FRS and FSP is same. These two forces, the line of action is same but opposite to each other. So they nullify each other. Means these two forces have no impact on the loop. So what is left? These two forces, P, Q and FRS. So it comes out to be like this. One is direction is like here, FPQ, and this is FRS. Practical situation is like this, and this is the width of it. Name it Q or R, I could say, like. So this is the practical situation. What we got, two equal, opposite and parallel forces are acting on each other. So they are forming a couple. What we got? Two equal, opposite and parallel force. Are acting on RS side, RPQ, QR side, I could say, of the loop. So they form a couple, and the moment of couple will produce a torque. So because of this formation, a torque is produced which tries to rotate the loop inside the magnetic field. Suppose it is making angle theta, let it be O. Then the moment of couple in physics, it gives you torque, tau, and moment of couple is nothing but any one of the force multiplied by the perpendicular distance. So force is use either FPQ or FRS, and perpendicular distance is OQ. This one, this OQ will be tau, comes out to be F is I BL, and OQ is QR sine theta. Use it here itself. Sine theta is perpendicular over hypotenuse. Perpendicular is OQ and hypotenuse is QR, right? and this comes out to be I B L, and QR sin theta is nothing but B sin theta, right? Remember, from this you can calculate OQ is equal to QR sin theta, and QR is B sin theta. Substitute this value, right? So what we got, tau is equal to I B L into B sin theta, where L into B is nothing but A, area of the loop. Let N be the number of turns in the loop, then tau comes out to be N I B A sin theta, or tau equal to N I A B sin theta. This will be the torque experienced by a current carrying loop inside a uniform magnetic field, where N is the number of turns, I is the current, A is the area of the loop, B is the magnetic field, right? And theta is the angle formed by the magnetic field with respect to normal of the surface, right? Mathematically, if I want to write down in vector formation, it will be Ni B cross A will be the torque, right? So what we got, when a current carrying loop is placed inside a uniform magnetic field, it is experiencing a torque on it, which is trying to rotate the dipole, rotate the loop inside the magnetic field, right? Just in analogy to this, if you do remember, the torque experienced by an electric dipole, the first unit inside an electric field, we are having tau equal to PE sin theta. Let it be 1, let it be 2. If you compare these two, what is happening? This E is the electric field, here we have got magnetic field, sin theta, we have got sin theta, but in place of this NIA we were having P, right? By just comparing these two equations, where P was given the name, if you do remember, electric dipole moment. Just in analogy to this NIA is given a new name, we denote it by capital M, and it is known as magnetic dipole moment. So the torque experienced by the loop can be written as tau equal to MB sin theta, right? It means what? This current carrying rectangular loop is just an equivalence of a magnetic dipole, as it was an electric dipole. So we can say this loop, current carrying loop, is an equivalence of a what? Dipole magnet. That is bar magnet. Means this loop can be considered to be just an equivalence of a bar magnet. What is a bar magnet? Simple and natural magnet, like this, having two poles, north and south, right? So I can conclude this article by saying that the torque experienced by a bar magnet, dipole magnet means bar magnet, inside a uniform magnetic field, tau equal to mb sin theta, where this m we got as NIA, the magnetic dipole moment, and so far as unit is concerned, its unit will become ampere meter square, right? And if I consider small m as the pole strength and 12 be its length of the bar magnet, then this m can be written as small m into 12, where this small m is pole strength. Be careful, it's just on the basis of analogy only. Pole strength, as we were having charge there, here it is pole strength. Most of the time they do ask write down the unit of pole strength. So what is pole strength here? It will become m by 12 magnetic dipole moment per unit length. Remember, magnetic dipole moment per unit length of a bar magnet. And so far as unit is concerned, for m it is ampere into meter square, and L means meter, so we are left with ampere meter. The unit of pole strength is ampere meter, remember. That's how we define. Means current carrying rectangular loop is just like a bar magnet placed inside a uniform magnetic field, and it experiences a torque tau equal to mb sin theta, right? And so far as magnetic dipole moment, its definition is concerned, we can define it by using this formula: tau is equal to mb sin theta. If theta be 90 degree, that is for the maximum torque, tau maximum will be mb, or m will be defined as tau max by b, right? Means the maximum torque experienced by a bar magnet when placed perpendicular to a unit magnetic field, right? And so far as the unit is concerned, its unit is ampere meter square. NIA, do remember that value, right? And if you use this one, 2 Newton meter and B Tesla, right? Or it can be Newton into meter per Tesla. Both are the same thing, right? It is now just equivalence to an electric dipole. All right. Thank you and have a nice day, right? Please, if you want me to continue this system, do subscribe our channel. Thank you.